Good morning, everybody. It's August 4th, 2026, and right now, roughly 50 miles off the coast of Oregon, there's a fault line lying completely silent under 2.5 miles of seawater that is capable of producing one of the largest earthquakes in recorded human history. And over the last several months, scientists have uncovered a stack of new findings that are forcing an uncomfortable reassessment of exactly how dangerous that fault really is. This is not old news repackaged. This is a genuinely new wave of research, 4 separate scientific developments landing within the same year. And when you put them side by side, they paint a picture that is more specific, more segmented, and honestly, more unsettling than anything researchers have published about this fault before. Here's what I need you to know about all of it. We're talking about the Cascadia Subduction Zone, the 600-mile-long megathrust fault that runs from northern Vancouver Island all the way down to Cape Mendocino in northern California, sitting directly offshore of Seattle, Tacoma, Portland, and dozens of coastal communities that are home to more than 10 million people combined. For decades, this fault has been called quiet, almost eerily so, which sounds like a good thing until you understand why silence at a subduction zone is actually one of the most frightening words in seismology. We're going to break down the new segmentation mapping that just identified the single most dangerous stretch of this fault, and it's not where most people assumed. We're going to get into a bizarre discovery of scalding fluid gushing out of the seafloor like a fire hose and why that fluid loss might be quietly increasing the friction and the risk along sections of the fault. We're going to cover brand new evidence that this fault and California's San Andreas Fault might be able to trigger each other within minutes, turning a regional disaster into a coast-wide one. And we're going to look at a companion study on a nearby fault system that found almost 0 warning signs before its largest earthquakes, which raises hard questions about how much notice anyone on this coastline would actually get. Stick around, because toward the end, we're also going to talk about what a preparedness researcher in Washington State just found when they modeled a worst-case tsunami scenario for a summer weekend, and the numbers are almost impossible to process. So let's start from the beginning and actually understand what this fault is and why it has earned its reputation as the most dangerous fault system on the entire West Coast. The Cascadia Subduction Zone is what geologists call a megathrust fault, and that term alone should tell you something, because megathrust faults are responsible for the largest earthquakes ever measured on this planet, including the 2004 Sumatra earthquake that triggered a tsunami killing over 200,000 people, and the 2011 Tohoku earthquake in Japan that we've talked about before in the context of how prepared a country can actually be. Cascadia works the same way those faults do. Off the coast of the Pacific Northwest, a slab of oceanic crust called the Juan de Fuca Plate is being forced underneath the much larger North American plate in a process called subduction. Normally, when 2 plates grind past each other, you get small, frequent earthquakes releasing pressure gradually, kind of like a rusty hinge that creaks every time you open the door. Cascadia doesn't do that. Instead, the 2 plates have become locked together by friction, essentially welded in place, and they are not slipping smoothly. Down at depth, the plates are still moving relative to each other, the Juan de Fuca Plate continuing its slow-motion journey beneath the continent, but the locked shallow section cannot move with it. That mismatch does not disappear. It gets stored as elastic strain in the crust, the rock itself bending and compressing like a spring being wound tighter and tighter for centuries at a time. Then, when the accumulated stress finally exceeds what the locked section of rock can hold, the whole thing lets go at once, and hundreds of years of stored energy releases in a matter of minutes. The last time that happened was the night of January 26th, 1700. We actually know the date with startling precision, and the way scientists figured it out is one of my favorite detective stories in all of Earth science. There are no written records from that era along the Pacific Northwest coast because the region wasn't yet documented by European settlers. Instead, researchers pieced it together from 2 independent lines of evidence thousands of miles apart. On this side of the ocean, geologists found entire coastal forests that had suddenly dropped several feet in elevation and drowned in salt water, creating what are now called ghost forests. Dead cedar trunks, still standing along the Washington and Oregon coastline, killed instantly by subsidence and then preserved by the cold, low-oxygen environment. Tree ring dating on those trunks showed the trees died sometime after the growing season of 1689. Meanwhile, on the other side of the Pacific, Japanese historical records kept by samurai administrators and merchants documented what they called an orphan tsunami, a set of unusually large waves that struck the Japanese coastline without any local earthquake to explain them. Nobody in Japan felt shaking. They just watched an unexplained wall of water roll in. Once researchers cross-referenced the timing, they realized the orphan tsunami and the drowned forests were the same event, a magnitude 9 earthquake off the Pacific Northwest coast that sent a tsunami racing across the entire Pacific Ocean and slamming into Japan roughly 10 hours later. That's the kind of energy we're talking about with this fault, And according to the geological record, this isn't a rare occurrence for Cascadia. Sediment layers pulled from the seafloor, called turbidites, show evidence of at least 19 earthquakes greater than magnitude 9 over the last 10,000 years. This fault has done this before, repeatedly, and it will do it again. The only real question that has kept scientists up at night is when, and increasingly, exactly where and how. That brings us to the first major piece of new research, and this one completely reshapes how scientists think about this fault's structure. For most of the last several decades, Cascadia was treated more or less as one continuous fault line, 600 miles of essentially uniform risk running from Vancouver Island down to Northern California. But a major mapping expedition using a research vessel that spent over a month collecting data offshore, sending powerful sound pulses down through the seafloor and reading the echoes the same way a doctor reads an ultrasound, has produced the most detailed subsurface map of this fault ever created. And what it found is that Cascadia isn't one continuous structure at all. It's made up of at least 4 distinct segments, each shaped by different rock types in the overlying continental plate, some denser, some more pliable, causing the incoming oceanic plate to bend and twist differently depending on where you are along the coast. Some segments plunge downward at a steep angle. Others slide in at a shallow, almost gentle angle. And that difference in geometry turns out to matter enormously because the roughness and angle of that boundary directly controls how a rupture could behave, whether it stays contained to one section or barrels through multiple segments at once. Here's the part that should get your attention if you live anywhere near Tacoma, Seattle, or the Olympic Peninsula. Out of those 4 segments, researchers identified the stretch running offshore of Washington State and southern Vancouver Island as likely the most dangerous of the entire fault. That segment is both shallower and smoother than the others, meaning it's more likely to slip all at once in a single unified rupture rather than breaking up into smaller, more manageable pieces. And because the subduction angle there is so shallow, the earthquake-producing interface doesn't stay safely out at sea the way it does along other parts of the fault. It appears to extend directly underneath Washington's Olympic Peninsula, essentially bringing the danger zone from offshore right up onto land. One of the researchers involved in the study put it about as plainly as a scientist ever will, saying that for cities like Tacoma and Seattle, this shallow extension could be the difference between an earthquake that is alarming and one that is outright catastrophic. Think about what that actually means for a second. This isn't an abstract offshore hazard anymore for that stretch of coastline. The fault zone potentially runs beneath populated land, which changes the entire risk calculation for how violently the ground could shake in some of the most densely populated parts of the Pacific Northwest. Now, segmentation on its own could actually be read as slightly reassuring news, because if the fault genuinely breaks into 4 somewhat independent sections, that opens the possibility that a future earthquake might rupture only one segment rather than the entire 600-mile length at once, producing something smaller than a full magnitude 9 event. But the researchers were careful to note that this is not a guarantee. It's still entirely possible for a rupture to jump across segment boundaries and cascade through several, or even all 4, sections in a single event, especially if the stress has been building simultaneously across multiple parts of the fault. And that uncertainty, whether the next Cascadia earthquake will be a contained regional event or an entire margin, coast-spanning catastrophe, is exactly why the second piece of new research matters so much, because it starts to answer the question of what's actually happening to the stress levels inside that fault system right now, in real time. This next discovery is one of the strangest and most consequential findings to come out of Cascadia research in years, and it started almost by accident. A research cruise studying the seafloor about 50 miles off the coast of Newport, Oregon, was delayed by weather, and while waiting, the crew used the ship's sonar to scan the surrounding seafloor and noticed something they weren't expecting: unusual plumes of bubbles rising from a spot roughly 3/4 of a mile beneath the surface. When they sent an underwater robot down to investigate, they discovered something researchers say has never been documented before at any subduction zone on Earth. It wasn't just methane bubbles seeping out of the sediment, which is a fairly common and unremarkable thing to find on the seafloor. It was warm, mineral-rich, nearly fresh water gushing out of the seafloor with the kind of force one of the researchers compared to a fire hose. They named the site Pythia's Oasis. Measurements taken on later expeditions showed the fluid emerging from the seafloor was about 9 degrees Celsius warmer than the surrounding seawater, and calculations based on the chemistry of that fluid suggest it's coming from roughly 2.5 miles beneath the seafloor, straight from the Cascadia megathrust itself, where temperatures are estimated to run between 300 and 500 degrees Fahrenheit. To put that in perspective, this is essentially deep fault fluid finding a pathway up through the crust and escaping directly into the ocean. And according to the researcher who led the investigation, it's the highest liquid leaking rate ever recorded at any subduction zone on the planet. Now here's why this matters far beyond just being a strange oceanographic curiosity. Fluid pressure between the two tectonic plates plays a critical role in how much friction exists along the fault. When fluid pressure between the sediment particles is high, it essentially acts like a lubricant, allowing the plates to slip more easily and release stress in smaller, more frequent increments. But when that fluid escapes, whether through a natural pathway like the one discovered at Pythia's oasis, or through the network of smaller strike-slip faults that seem to be venting it, the loss of that fluid pressure increases friction between the oceanic and continental plates. More friction means the locked sections of the fault can hold on to stored stress even more tightly before they finally fail, which in turn means more energy potentially gets banked before an eventual rupture. Researchers have been careful to say this discovery doesn't mean an earthquake is imminent, and it doesn't fundamentally change the currently understood probability of a major Cascadia earthquake happening tomorrow versus 50 years from now. But it does reveal an entirely new mechanism at play beneath this fault that scientists didn't even know existed until a few years ago, and follow-up research building on that discovery has continued to track how fluid distribution varies along different parts of the subduction zone. A more recent University of Washington study, using 13 years of ground motion data collected from offshore sensors, the first extended offshore monitoring effort of its kind at Cascadia, found that the plates along this fault may not be uniformly locked the way scientists long assumed. The northern portion of the fault appears locked and seismically quiet, consistent with stress steadily building toward a future rupture. But the central region shows evidence of slow slip events and fluid movement, essentially small, almost imperceptible releases of stress that happen too slowly to be felt as an earthquake. What that means is that different sections of this fault may currently be behaving in fundamentally different ways, some quietly and steadily loading up stress, others periodically bleeding off small amounts of it, and untangling which of those patterns dominates where is now one of the most active frontiers in earthquake science on this coast. Let's talk about the third development, because this is the one that genuinely changes the scope of the worst-case scenario. For years, researchers have generally studied Cascadia and the San Andreas Fault as separate systems. Cascadia handles the Pacific Northwest, the San Andreas handles California, and while everyone acknowledged they're both part of the same broader tectonic picture along the Pacific Rim, they were treated as largely independent hazards, with their own separate timelines. New research published this year has upended that assumption. Scientists studying sediment layers formed by underwater landslides, deposits that build up over thousands of years and preserve a record of past seismic shaking, found unusual patterns, suggesting that a major Cascadia earthquake and a major San Andreas earthquake may have ruptured close together in time, possibly within minutes to hours of each other in the geological past. The proposed mechanism is what researchers are calling synchronization, essentially the idea that a massive rupture along Cascadia sends a pulse of stress southward through the crust that's strong enough to nudge an already stressed section of the San Andreas Fault past its own breaking point, triggering a second, independent earthquake almost immediately afterward. Think about what that actually means for a worst-case scenario along this coastline. Instead of a single, contained disaster centered on the Pacific Northwest, you could be looking at two major fault systems failing in extremely close succession, meaning cities from Vancouver Island down through Seattle, Portland, and potentially into Northern California and the Bay Area could all be dealing with major earthquake damage within the same 24-hour window, all while emergency resources, hospital capacity, and search and rescue teams are already stretched thin responding to the first event. Emergency planners have spent decades building disaster response models that essentially treat Cascadia and San Andreas as sequential, separate problems that could theoretically be handled with resources shifted from an unaffected region to an affected one. This new evidence suggests that assumption might not hold in every scenario, and that a truly worst-case West Coast earthquake sequence could functionally be a multi-state, multi-city catastrophe, unfolding almost simultaneously rather than in a manageable sequence. Researchers are clear that this doesn't happen every single time either fault ruptures, and it's not being framed as an inevitability, but the geological evidence that it has happened before is now strong enough that emergency management agencies are being urged to start factoring a synchronized rupture into their planning as a realistic possibility rather than a remote and dismissible worst-case scenario. Now, let's shift slightly north of the main Cascadia interface and talk about a companion piece of research that, in some ways, is the most unsettling finding of the entire year, because it strikes directly at the question of warning time. Just south of the main Cascadia zone sits the Mendocino Triple Junction, the point off the coast of Northern California where three major tectonic boundaries intersect: the Cascadia Subduction Zone, the San Andreas Fault, and the Mendocino Fault, all converging in one geologically chaotic patch of ocean floor. It's one of the most seismically active and structurally complicated regions on the entire continent, and a new study focused specifically on the Mendocino Fault delivered a conclusion that should worry anyone hoping for advance notice before a major offshore earthquake. Researchers examined some of the largest earthquakes ever recorded along the Mendocino Fault, including a powerful magnitude 7 event that struck in December of 2024, one of the strongest oceanic transform fault earthquakes ever documented in that region, and looked specifically for foreshocks, the smaller tremors that sometimes, though not always, precede a major earthquake and can occasionally serve as an early warning sign. What they found was that these large Mendocino earthquakes showed almost no meaningful foreshock activity beforehand. The fault stayed essentially silent right up until the moment of rupture. This challenges an assumption that a lot of earthquake science has quietly leaned on for years, the hope that certain offshore fault systems might display a recognizable buildup pattern, a detectable increase in smaller tremors that scientists could eventually learn to read as an early warning signal. If large earthquakes along a major fault directly connected to the Cascadia system can strike with essentially no seismic buildup at all, it raises the very real possibility that a major Cascadia rupture itself could arrive the same way, with no meaningful precursor signal for scientists to catch in the hours or days beforehand. That doesn't mean earthquake early warning systems are useless. Systems like Shake Alert, now operational up and down the West Coast, work on a completely different principle. They don't try to predict an earthquake before it starts. Instead, they detect the fast-moving but low-energy P waves generated the instant a rupture begins and race that detection to populated areas ahead of the slower, more destructive S waves that actually cause the violent shaking. That can still provide anywhere from a few seconds to slightly over a minute of warning depending on your distance from the epicenter, which is genuinely valuable time. Enough to drop and take cover, enough for a surgeon to pause a procedure, enough for a train to begin braking before a bridge. But the Mendocino findings underline something important. That warning comes after the rupture has already begun. It is not advance notice that a rupture is coming. And if researchers can't find reliable long-range precursors along a fault system this closely tied to Cascadia, that's a sobering data point for a region that has been hoping science might eventually find a way to see the big one coming before it arrives. While all of this offshore research has been unfolding, there's also been a steady drumbeat of smaller reminders that this fault system isn't some distant, dormant abstraction. Just this past June, 3 moderate earthquakes rattled the seafloor near the Blanco fracture zone off the Oregon coast, the strongest reaching magnitude 5. 7 striking roughly 100 miles west of Pistol River. None of them triggered a tsunami warning and none caused significant damage, but each time this happens, it reinforces the same underlying message that seismologists have been repeating for years. That one of North America's most dangerous fault systems sits just off this coastline, quietly active and impossible to ignore for long. And it's not only the offshore megathrust drawing renewed attention. Newer research on the Seattle Fault Zone, a network of shallower faults slicing directly through the lowlands beneath Puget Sound, found that smaller secondary faults within that system appear to rupture roughly every 350 years, a far more frequent cycle than the massive main fault that has historically drawn most of the scientific attention. That's a meaningfully shorter interval than the centuries-long recurrence pattern for the offshore megathrust, and it means the greater Seattle area is potentially facing seismic risk on 2 very different timelines simultaneously, a slow-building megathrust offshore and a faster cycling network of shallow crustal faults running underneath the city itself. Let's talk for a moment about what an actual rupture along this fault would look like on the ground, because the scale is genuinely difficult for most people to fully picture. A magnitude 9 earthquake along Cascadia wouldn't be a sudden jolt lasting a few seconds, like the moderate earthquakes most people have experienced. Subduction zone earthquakes of this size produce shaking that can last anywhere from 6 to 10 minutes, an almost unimaginably long duration if you've never experienced one, because the rupture has to travel along hundreds of miles of fault before it finishes. Emergency planning documents built around this scenario describe expected ground shaking that would be severe across virtually the entire Interstate 5 corridor, from Vancouver Island down through Seattle, Tacoma, Portland, and into Northern California, affecting a population of well over 10 million people. Older buildings not built to modern seismic codes, unreinforced masonry structures, older bridges, and soft-story apartment buildings are all considered highly vulnerable in this kind of prolonged, severe shaking. And that's before you even get to the tsunami. Because, unlike a typical crustal earthquake, a Cascadia megathrust rupture wouldn't just shake the ground, it would violently and suddenly displace the seafloor itself across hundreds of miles, generating a tsunami capable of reaching coastal communities in the Pacific Northwest in as little as 15 to 20 minutes. Far too fast for any official warning system to matter for people living directly on the coast. That's why the standard guidance in this region has always been that if you feel strong or prolonged shaking near the coast, you move to higher ground immediately without waiting for an official alert, because the ground shaking itself is the warning. A recent study conducted by Washington State's Emergency Management Division, using updated census data and building inventories, modeled what researchers called a reasonable worst-case scenario, a magnitude 9 earthquake striking at 2 in the morning on a summer weekend. when coastal tourist populations are at their highest, and most people are asleep and unprepared to react quickly. The resulting casualty projections were described by the researchers involved as staggering, a significant escalation from earlier federal estimates. And those earlier federal estimates were already sobering enough on their own. A federal emergency planning document modeling the full scenario across Oregon and Washington projected that a magnitude 9 Cascadia earthquake and tsunami happening today could kill an estimated 14,000 people and injure over 100,000 more, with economic damage across Washington, Oregon, and Northern California potentially exceeding $70 billion. Some of those injury estimates come specifically from combining direct earthquake trauma, tsunami-related injuries along the coast, and the secondary wave of harm caused by aftershocks, ruptured hazardous material sites, and contaminated water supplies in the weeks that follow. And remember, those federal figures are considered by many state-level researchers, including the team behind the more recent Washington State study, to actually be conservative compared to what updated population and building data now suggest. So where does all of this leave the actual probability question, the one everybody watching this ultimately wants answered, which is simply, how likely is this in our lifetime? Scientists studying the fault have broken the risk down by scenario rather than giving one a single number, because the fault doesn't have to rupture along its full length to produce a major disaster. If only the southern portion of Cascadia ruptures, researchers estimate the resulting earthquake would land somewhere between magnitude 8 and 8.6. They place the odds of that happening within the next 50 years at roughly 37 to 43%. If the entire margin ruptures at once, a full-length event producing something in the magnitude 8.7 to 9.2 range, the same kind of event that struck in 1700, researchers currently place those odds at somewhere between 16 and 22% over the same 50-year window. Those aren't numbers that mean this is happening next Tuesday, but they aren't numbers that let anyone comfortably ignore this fault either, especially when you consider that the interval since the last full rupture, over 325 years now, sits well within the range. This fault has demonstrated it's capable of building toward before letting go. It's also worth pointing out how these different pieces of research actually reinforce each other, rather than sitting as isolated, unrelated findings. The segmentation study tells us where along the fault the geometry is most favorable for a single unified rupture. The fluid escape research gives us a plausible mechanism for why stress might be accumulating unevenly along different stretches of that same structure. The San Andreas synchronization evidence tells us the consequences of a rupture might not stay contained to the Pacific Northwest at all. And the Mendocino foreshock study tells us not to expect much warning when any of this finally happens. Individually, each of these studies would be interesting but limited. Together, they start to form something closer to an integrated picture of how this fault actually behaves. And that kind of cross-referenced understanding is genuinely new. For most of the modern history of earthquake science on this coast, researchers were working with fragments, a rough sense of recurrence intervals pulled from sediment cores, a general understanding that the fault was locked and not much else. What's happened over the last couple of years is that ocean floor cable networks, extended offshore monitoring, and repeated survey cruises have finally started generating the kind of dense, continuous data set that lets scientists move from broad assumptions to specific, mapped answers about where the danger actually concentrates. What's genuinely different about this moment in Cascadia research, compared to where the science stood even 5 or 6 years ago, is the level of resolution scientists are now working with. This fault used to be studied as one long, largely uniform hazard zone. Now researchers can point to a specific segment off Washington State and southern Vancouver Island and say this particular stretch appears smoother, shallower, and more likely to rupture as a single unified block, extending its dangerous zone directly beneath populated land on the Olympic Peninsula. They can point to a specific seafloor location 50 miles off Newport, Oregon, and explain how fluid, escaping from deep within the fault, might be quietly ratcheting up friction in ways nobody had documented before. They can point to sediment cores that suggest this fault. And California's San Andreas may not be as independent from each other as everyone assumed, and they can point to a neighboring fault system that shows almost no warning before its biggest earthquakes, a sobering data point for anyone hoping science is close to genuinely predicting when Cascadia will finally let go. None of these findings individually proves that a major earthquake is coming soon, but stacked together across a single year of research, they represent one of the most significant leaps in understanding this fault system as seen in a long time. And they all point in the same uncomfortable direction, toward more segmentation, more complexity, more interconnected risk, and less certainty about exactly how much warning anyone along this coastline will actually get. The most important thing to understand is that none of this uncertainty is a reason for panic, but it is absolutely a reason for preparation, and that distinction matters enormously. Unlike a supervolcano scenario or some kind of speculative doomsday event, this is not a hypothetical. This fault has ruptured at least 19 times in the last 10,000 years. It produced a magnitude 9 earthquake a little over 3 centuries ago that we can date almost to the exact night. And every single researcher working on the system agrees it will do it again. The only genuine debate is about timing, segmentation, and scale. If you live anywhere along this stretch of coastline, from British Columbia down through Northern California, the practical steps are the same ones that apply to any major seismic risk zone, and they're worth actually doing rather than just hearing about. Know whether your home or workplace sits inside a tsunami inundation zone, and know your evacuation route to higher ground without needing to check a map in the moment. Keep enough emergency supplies, water, food, medication, and first aid to get through at least 72 hours, since major infrastructure damage after an event this size could easily delay outside help for days in the hardest hit coastal areas. Secure heavy furniture and water heaters, know where your gas shutoff valve is, and put together a communication plan with your family for a scenario where cell networks are down for an extended period. These are small, unglamorous steps, but they are exactly the kind of preparation that separates a survivable disaster from an unmanageable one. And that gap has been proven again and again in earthquakes around the world. What do you think? Does the new segmentation data change how you think about the risk along this coastline? And do you think emergency planners are moving fast enough given what scientists are now finding? Let me know your thoughts down in the comments. I genuinely love to hear from anyone watching this who actually lives along the Pacific Northwest coast and how seriously this gets talked about where you are. If you found this breakdown useful, go ahead and drop a like on this video. It genuinely helps push this kind of research in front of more people who need to actually see it. And if you're new here, consider subscribing, because we're going to keep tracking every new study that comes out of this fault system as the data keeps evolving. Feel free to share this with anyone you know living in Seattle, Portland, or along the coast, because honestly, most people in this region have heard the phrase "the big one" thrown around for years without ever hearing the actual science behind why researchers are getting more specific and more concerned about exactly where and how it's most likely to happen. Thanks so much for watching. We'll keep following this story as more research comes in, and we'll see you in the next one.